Bismillahirrahmanirrahim. In this video, we will discuss some of the examples related to the DC machines. So, our first example is related to the DC series motor that is drawing 20 ampere at 110 volt and is running at 800 rpm. The armature resistance is 0.1 ohm and the field resistance that is connected in series with the armature is 0.05 ohm. We are supposed to determine the motor output power in horsepowers and the torque developed at the armature if the iron and friction losses are 50 watt. Okay, so first step, as I have already discussed in the previous tutorial session, is to draw the circuit diagram to understand the problem. So here you can see the armature circuit. Armature circuit is this one, A1 and A2. You can assume armature resistance is 0.1 ohm and this armature is basically rotating in the magnetic field and it is rotating at the speed omega and the induced torque is T induced and the load torque will be opposite to this one that is connected over here, and this is representing the back EMF in our machine that is equal to certain value based upon the motor parameters. So shortly we will calculate that one, and this one is the field winding, F1 and F2 or D1 and D2 different symbols are used. So this is this series which will be series winding because it will be connected in series with the armature. So in the lab machines it is usually marked as D1 and D2. It is different from F1 and F2 because F1 and F2 are usually used for the shunt machine and the separately excited machine, that's the high resistive winding, but the series winding is usually represented as D1 and D2 and that has the low resistance, and in this particular example it is 0.05 ohm. Okay, so our terminal voltage is 110 volt over here. So first of all, we are going to look at the input power that we are going to apply to the machine, and we are given that it is operating at 20 ampere at 110 volts. So power is the product of the current and the voltage. So 20 ampere into 110 volts, so machine is going to take 2200 watt as an input at this particular state, and it is running at 800 rpm when you are going to apply 110 volt and it is taking 20 ampere and taking the input power of 2200 watt. Okay, now let's calculate the back EMF. Back EMF, as discussed in the previous tutorials, very important factor. So first of all, you will have to write down the motor terminal equation. So this voltage Vt will be equal to the IARF, the voltage drop over here, plus IA into RA, the voltage drop over here, N plus back EMF. Sum of all of these voltages must be equal to the terminal voltage, right? We are not considering the inductances over here because there is no voltage drop across that one. They are considered short circuit in the DC, and we are going to assume that there is a constant current over here. So terminal voltage should be equal to that. So how to find out this back EMF? Terminal voltage Vt minus this voltage drop minus this voltage drop, and that you can see over here. Terminal voltage minus IARA minus IARF. So it can be written like this. So now if we plug in the values over here, the terminal voltage, armature current, armature resistance, field resistance, so 107 volts. So that is the back EMF at this particular condition when machine is running at 20 ampere with at 800 rpm. So this armature current is basically based upon this one because this is the voltage over here and the voltage over here is Vt. The difference of these two voltages is basically injecting the current, that is the armature current over here. If this difference is going to increase, the armature current is going to decrease, and if the difference is going to decrease, then the armature current is going to decrease. So back EMF plays a very important role to change the current, and because of the change of the current, the torque in the series machine, that is equal to Ia square, Kia square, proportional to that. So as the armature current is going to change, the induced torque is going to change. Similarly, this back EMF is very important in many other analysis of the machine. Okay, so coming towards the power that is converted into the mechanical form. So once you apply the power to at the terminal, some power loss will be over here. That will be calculated as IF square into RF, that is the copper loss across the field winding. Some power loss over here, IA square into RA, copper loss across the armature winding. The remaining power will be converted into the mechanical form, so we call it the electromagnetic power, and can be determined in the number of ways. The easiest way is to take the product of EB and the armature current. The current passing through this one, right, and the voltage over here. Other way around is that take this input power minus this loss I f square into Rf minus this loss Ia square into Ra. The remaining power that is left, that will be over here. So we will be using this Eb into Ia. So that's the power that is converted into the mechanical form. So 107 volt is the back EMF over here, and then 20 watt, 20 ampere is the current. So the power is 2140 watt over here, that is converted into the mechanical form. And the power over here, it is a product of the voltage and the current. So that is 20 ampere into 110 volt, 2200 watt. So you are injecting 2200 watt power, but out of that 2140 watt is the power that is converted into the mechanical form. So it is not the load power, because we have not yet considered the mechanical losses. So out of this there will be the mechanical losses, and then the rest of the power will be available at the load that is connected over here with the shaft. Okay, so what will be the electromagnetic torque, the induced torque, you can say in some cases. So that will be determined by using the expression P is equal to T omega. But over here, if you are considering electromagnetic torque, electromagnetic power, and the machine speed. So the electromagnetic torque will be calculated by looking at the electromagnetic power, the power converted into the mechanical form. So PEM over omega m, 2140 watt converted power, 800 rpm is the speed given to us. To convert it into radian per second, because over here in this expression you need the values in the radian per second. So 2 pi by 60. So the load torque will be 25.54 Newton meter, and this is given to us that machine is running at 800 rpm, right, at this particular condition. That's why we are going to consider this speed. So 800 rpm into 2 pi by 60. So machine is delivering this much torque, that is 25.54 Newton meter, that is available at the shaft. Okay, now let's look at the losses which are going to take place in your machine. We have calculated the electromagnetic power directly looking at this, but we can do other way around as well, that we can calculate these ones and we can subtract it from the input power to get the output power. So what will be the copper loss? We call it the copper loss. Why? Because this is the loss in the copper winding, right? So Ia square into Ra, that will be the loss in the armature, and Ia square into Rf, that will be the loss in the field winding. So 20 ampere is the current, because the current will be same in the armature and the field, because they are connected in series. So 20 square into 0.05 plus 0.1, so 60 watt. So we applied 2200 watt and 60 watt is the loss. The rest you can see over here, 2140 watt is the power that is converted into the mechanical form. Okay, now what will be the total loss? The copper loss and the iron losses and the friction losses. So if you look at the statement over here, we are given that iron and the frictional losses are 50 watt. What are the iron losses? Those maybe you can say the sum of the hysteresis loss and the eddy current loss that is going to take place in the core of the machine, that is considered as the constant. Okay, so that we usually called it the iron loss. And the frictional losses are the mechanical losses, maybe because of the windage, maybe because of the friction somewhat. So all of those are given lumped together as a 50 watt to us in this particular example. So this is the copper loss, this is the frictional loss. A total loss is 110 watt. So the power that you are applying to the machine is 2200 watt. So from that you will have to subtract the total loss of 110 watt. So the remaining power is 2090 watt that will be available to the load. So power converted into the mechanical form was 2140, only 60 watt loss. That was the copper loss. And then over here the frictional losses, as those are given to us in the lumped form, that it is 50 watt iron losses plus friction. So we have subtracted this from this value, and the rest of the power is available at the load, right? So that power is 2090 watt. So to convert it into the horsepower, you are simply going to divide it by 746 watt, because 1 horsepower is equal to 746 watt approximately. So if you divide this power which is in watt by this 746, so 2.80 horsepower is the power that is delivered to your load, considering all the losses, right? So we can make a power flow diagram as well. We have given the input power, from that we subtracted the copper losses, and these were Ia square Ra, and the second one was If square into Rf, and in the series machine these two are same, then minus the iron losses, those are the hysteresis and the eddy current losses, minus the mechanical losses, and then the stray losses. So rest of the power will be available at the output. So these are given lumped together in this particular case as the 50 watt. Okay, now our next example is related to the self-excited DC shunt motor, that is basically a shunt type machine. So it is running at 1000 rpm and it is drawing an armature current of 25 ampere. So we need to determine the speed if the torque has to be doubled. The applied torque has been doubled, so armature resistance is 0.2 ohm. So we need to look at that, what will be the speed if we double the torque on the machine. So first of all, again to draw the equivalent circuit. So equivalent circuit is shown over here, as it is a self-excited machine or the shunt machine. Shunt machine is also called self-excited because it's take the power from the same source. So the armature current that is known to us, that is 25 ampere, and armature resistance is given to us 0.2 ampere. These are the armature terminals A1 and A2, and at that machine is running at 1000 rpm. Field is connected in parallel, right? F1 and F2 terminals, and 110 volts are applied to the machine. Okay, so again we are going to look at the back EMF first of all, that what will be this back EMF at the given condition, and that will be determined by this one, Vt minus IaRa, because it's a shunt machine. So terminal voltage minus armature current into I into Ra, 25 into 0.2, so 105 volt. That's the back EMF that is available over here. Okay, for shunt machine we have discussed in the theory class that the torque is given as KIFIA. So as field current is not changing, field current is constant because our applied terminal voltage is constant. So we can mark it as constant, and let's suppose that is KT into IA1. So the torque at that particular condition. Okay. Now the torque at when you are going to double the torque, of course that is going to change. The armature current double current will be required. Okay, so the torque will be given by this equation, that KIA2 into KIA2, that will be equal to the new torque T2. So the ratio of these two, T1 divided by T2, that will be equal to IA1 over IA2. Basically what we are going to do, so we have divided these two equations. Torque 1 is equal to KIA1 divided by torque 2, that is equal to KIA2. So the change in the torque will be equal to the ratio of the change of the torque is equal to the ratio of the change of currents. So from here you can work out the new armature current, and new armature current will be of course double because our torque is double. So new current that is required is the 50 ampere, and for that of course this back EMF will have to adjust itself. It will have to change to, so that the new armature current is established, that is 50 ampere. Okay, so now we need to work out this new back EMF. So for that you can see the expression over here, Vt minus Ia2 into Ra. So 110 volt, 50 into 0.2, so 100 volt. So if you observe, compare these two over here, it was 105 ampere, 105 ampere the back EMF over here, and now the back EMF is 100 volt. So because of that the current in this branch is 50 ampere. The current is doubled, that's why the torque will be doubled, because for a shunt machine torque is proportional to the armature current provided your field current is kept constant. So double the torque, double the armature current, and for the double armature current this back EMF needs to be 100 volt. Right. Okay, now using the comparison that we have done in the previous tutorials as well, so EB1 that will be equal to K times flux into N1 divided by EB2, that is equal to K flux into N2. Flux is same, so that will be cancelled out. So from here we can say that EB1 over EB2, that is equal to N1 over N2. So now you can work out what will be the speed, new speed N2, because we know about the back EMFs. We know about this back EMF, we know about this back EMF and the initial speed, so we can work out the N2 that is given by this expression, that is equal to EB2 by EB1 into N1. So now just plug in the value, 100 volt back EMF, 1000 RPM, and the new back EMF is 105. sorry, at 25 ampere it is 105, and at 50 ampere it is 100 volts. So the new speed will be 952.38 rpm. So when you are going to double the load, the current is to be doubled, the back EMF is going to change, and your machine is now going to run at 952 rpm instead of the 1000 rpm at which it was running when the current was 25 ampere. So when you apply the load on the machine, the current increases and the back EMF is adjusted at the new value, and the speed gets dropped, and all of those we have calculated in this example. So that's all from this video. Thank you very much.